Mclaren and Taylor series are examples of a classification of series we call power series, which we're going to define now. A power series centered at x equals 0 is of this form, which if we write a couple terms out looks like so. A Mclaren series is a special type of power series centered at x equals 0 in which the coefficient is a specific value, specifically the kth derivative at 0 divided by k factorial. A Mclaren series is an example of a power series centered at x equals 0, but not every power series centered at x equals 0 is a Mclaren series. Similarly, we can define a power series centered at x equals a, which is of this form, which if we write a few terms out, looks like so. A Taylor series is a power series centered at x equals a, but again, not every power series centered at x equals a is a Taylor series. We have a series here, and we're asked to write the first couple of terms out. This is a power series centered at x equals 0 because it's of the first form that I showed. So the first term would be x to the 0 plus x to the 1 plus x to the 2 plus x to the 3, etc. And I'll actually notice that this series is a geometric series in which we are multiplying by an r value of x. So our r value is x. And we know that a geometric series converges if the absolute value of r is less than 1. In other words, in this case, if x is between -1 and 1. And this we call the interval of convergence. And the distance from our center, remember that our center was x equals 0, to our outside point, that is called the radius of convergence. So in this case, our radius of convergence is 1. By the way, you could have used the ratio test for absolute convergence to come up with the interval of convergence. It's just that we knew that this was a geometric series, and so we know that the r value is between -1 and 1. Now we're also asked to find what the sum of this series is when it converges. Well, when it converges, we know that this will equal a over 1 minus r. And the first term of our series is 1 over 1 minus r, which is x. And so this series converges to this as long as x is between -1 and 1. In other words, the infinite series is equivalent to this on this interval. Just a couple of important points to note with power series. First of all, the convergence of a power series depends on the value of x. Finding when the series converges is called finding the interval of convergence. Usually you will use the ratio test for absolute convergence to determine the interval of convergence. Although, as I said showed in the last example, we knew it was geometric, so we were able to use the fact that the absolute value of r was less than 1. But usually you'll use this test. The third point is something new that I haven't specifically talked about, and that's that the interval of convergence will take one of three forms. If your center point for your power series is x equals 0, then your interval of convergence can be just that point itself, x equals 0. It can be an interval an equal distance on both sides of your center point, from negative r to r, or it can be all real numbers. Your interval of convergence will always take one of those three forms. If it's centered at x equals a, then it can just be the center point x equals a, or it can be r units away from a, so a plus r or a minus r, so there's your interval, or it can be all reals. And remember that your radius of convergence, which we typically use as capital R, is the distance from the center to the outer point of the interval of convergence. So if your interval of convergence is just the center point, the radius of convergence would be 0. If it's of this form, your radius of convergence is r, and if it's all reals, then it's infinity. All power series have an interval of convergence of one of these three forms. In the last example I did, it had a form between negative 1 and 1, which was this. In the last video, when I checked the interval of convergence for sine x, we found it was all reals. But it can also be just the center point in some situations. The last thing I need to emphasize, though, with the interval of convergence is that you must check the endpoints of the intervals of convergence separately to determine if they're included in the interval of convergence or not. So even though I've shown this to be an open interval, in fact it may be a closed on both or either of the ends depending on the convergence at the endpoint. So you must check the convergence of the endpoints separately, and I will do that in the example below. So in this example we have a power series centered at x equals 5. Be careful when you're looking at an infinite series to not conclude that it's an alternating series just by looking for the negative 1 to the k, because remember that x can make the terms of this series positive or negative, and so the terms do not necessarily alternate in sign. So we want to find the interval and radius of convergence. So first of all, to check the convergence, we know that for this infinite series to converge, the limit of the k plus first term over the kth term, the absolute value of that must be less than 1. I'm using my ratio test for absolute convergence. And so applying that, I can leave the negative 1 to the k out since I'm taking absolute value. There's the k plus first term divided by the kth term. Times the reciprocal of the denominator. And we know that it needs to be less than 1. So we want to simplify this. I can subtract the powers on this piece. I can subtract the powers here, which would leave me with a 4 on the denominator, times k on the top and k plus 1 on the denominator. And now I'm going to take my limit, which means that the 1 here won't be important. These will cancel out. And as k goes to infinity, I will then have this being less than 1. So I can write that like so, which means that x minus 5 is between 4 and negative 4. And if I add 5 to both sides, I've got two equations in one here. X is between 1 and 9. Now we need to be careful that we're not finished yet, because we need to check the convergence at 1 and 9 separately. So we must check convergence at x equals 1 and x equals 9 separately. So here's my original question again. So checking x equals 1 just means I'm going to plug 1 in for x. And on the numerator, I can combine the two terms to be 4 to the k. So those cancel out. And so my series becomes this, which I know is a harmonic series, which diverges. In other words, x equals 1 will make my series diverge. So this will not be part of my interval of convergence. If I check x equals 9, plugging 9 into here, that will mean that these terms cancel out. And I now have this, which I recognize as an alternating harmonic series, which we know converges. So x equals 9 is part of my interval of convergence. And so if I add that into there, therefore, interval of convergence is 1, not including 1, to 9, including 9. And my radius of convergence from 5, remember from our center point to the extremes, should be an equal distance. That is my radius of convergence. Radius of convergence is 4. And so I know my infinite series converges on this interval.